everyone. I'm Dr. Priyambada, Assistant Professor at IIIT Sri City. I'm going to chair this session, the second session of this International Research Workshop on Advances in Deep Learning and Application 2022. So today we have, for this session, we have Dr. Anand Mishra, who is a faculty member at the Department of Computer Science and Engineering and an affiliated faculty member at the School of AI and Data Science at IIT Jodhpur. Dr. Anand's group at IIT Jodhpur focuses on the problems intersecting vision, language, and knowledge graphs. Previously, Dr. Anand was a postdoctoral fellow at IISc Bangalore, where he worked with Dr. Parthav Talutkar and Dr. Anirban Chakraborty on knowledge-aware computer vision. Dr. Anand received his PhD from IIIT Hyderabad, working on scene text understanding under the supervision of Dr. C.V. Jawahar and Dr. Karthik Alhari. Dr. Anand is a recipient of the prestigious Microsoft Research India PhD Fellowship in 2012, the XRCI Doctoral Dissertation Award first runner-up in 2015, and IIT Jodhpur Teaching Experience Excellence Award in 2020. Recently, he was recognized as one of the outstanding reviewers at ICCV 2021. So without further delay, I would like to welcome Dr. Anand to proceed with his presentation on Introduction to Neural Networks and Deep Learning. So over to you, sir. So please. So I think it's not audible.
Okay, thank you, Dr. Priyambada. I'm not able to share my screen. Can you give me the right?
Yes, I will.
Anyone? So it says host disabled, participant screen sharing.
Okay, just a second.
Yes. If you can make me co-host, that should work, I guess.
Yeah. So did you get any?
Yes, yes.
Yeah.
No, I can see the screen.
Yes.
Yes. Okay. So just a minute.
Yes, sir, I hope you are able to share the screen now.
Yes, I can. Can you see my screen?
Yes, sir.
Thank you. All right. So good morning, everyone, and thanks, Dr. Priyambada, for kind introduction, and also thanks the organizing team for giving me opportunity to talk about a little bit of introduction to neural networks and deep learning. So this presentation is primarily more of an introductory presentation, and it's like getting into the basics of neural networks, which is really important to understand. And then as we move in this workshop, there are a lot of advanced talks even in today's and next 4 days. So take this as a very first lecture in neural network kind of, right? So with that, let me start this presentation. So I will be using various materials which are listed here, a few of my own example as well. So also I will share this with all of you so that you can have a look, and please feel free to ask questions in between as well, so that it's more of I want to make it more interactive. I've also log in from other screens, so I have 2 screens in front of me. So if if you either unmute or if you if you chat, if you write your questions in chat, that should work. All right. So another thing before we start, this particular talk, as I said, it's not the talk to become expert in this field. It is just a beginning of talk. I'll try to do basic understanding of how neural network really work, and then like how deep learning have originated. Okay, so if you see around in the research or in the computational science or computer science, majority of the time you see like deep learning is really taking over. It's a major thrust areas in various universities, various colleges, industries, academia, everywhere. Many of the new state of the art in many machine learning tasks are now deep learning based. So just to motivate, this is a data from a prestigious conference in machine learning, which is now called NeurIPS. Formerly it was known as NIPS. So these are two data points, which is showing in 2006 what was the trend and how that has changed in 10 years. That is 2016. How things have changed. So many times these are the terminologies used in this conference. Right? This is one of the most prestigious conference in machine learning, and how things have start changing. You can really see like learning networks, deep models, optimization. So these kind of terms are getting used more. That also means these are from the paper titles, right? So this also means that people have started working more towards deep learning in the last few years, and this has continued, and it's not stopped in 2016, though the data is about 16, but it has continued and is now really taking over. And not just the academic thing, deep learning has also shown a lot of things in the land, right? It's not just an academic lab thing, but it's also getting translated in various applications. For example, with fairly well accuracy, one can really find out what car model is there, or what is the vehicle model running in the road, and such things can have a lot of applications in road safety. With fairly well, you can not only recognize which car model is this, but maybe you can also read out what is written. So you may read out what is the license plate number, which type of car is this, and so on, and where is this car, right? So of course, these are not really, I would say, completely solved problem, but there is a lot of progress, and a lot of real applications are also coming out. You can fairly well recognize faces of celebrities and tag them, right? So that these are the things which are really coming up. Not only that, you can also describe the images as we human do. For example, I can given this image, these are the computer generated natural language description of this image, which looks very much close to what we as a human can describe, right? So a child in a helmet is riding a bike, or a group of people walking on a busy street. So all these are like the big bone model of these are deep learning models. Even you can translate languages from one language to another language. You can also fairly well recognize what is said in as an audio, right? So you say hello, and it's recognized. And all these are not just a research paper things, but they are getting translated, and many of us are really using them. Let's say, for example, many of us use Google Assistant and Siri. Such things are really getting used, right? So, and the backbone of many of these technologies are deep learning. So therefore, it's really important to learn this topic in detail, and the organizers have done a very nice job of organizing this workshop, where there is a series of talk, and this talk is primarily based will be on the basics of neural networks, right? So where the deep learning has originated. So we'll talk, I have divided this presentation into 4 modules. Module 1 will talk about history of this area, and a little bit of these things. Of course, Professor BKM also has talked some of these things. Then we will talk about how this inspiration from the biological neuron has influenced this area. We'll talk about a basic building block of deep learning, which is the fundamental block, perceptron. We'll then talk about how multi-layer perceptrons are more powerful, and we'll connect, like, this is how the deep learning models are getting built. How do you train them and all, right? So this is the structure of this talk. So let's get started with the history of neural networks. So neural networks are not the new things. Like, it has been there for a while. If you look into the literature, even in 1891, first time this neurologist called Vaughan, he has introduced this term neuron. Of course, when he introduced this term, he was not in the context of neural networks, but it was more of a context of a neurologist, right? So neurology. So this guy was actually a neurologist, and he used this term neuron, right? So this is way back in 1891. Long after that, there was a first neuron model, or neuron computational model. This is called McCulloch-Pitts neuron, or introduced by these two folks in 1943, right? And this was just a simple computational model, which was trying to mimic the neuron of our brain cells, right? So this is MP neuron, not much powerful. Then there was a perceptron model by Frank in 1957, 1958 times, which was, like, that time very powerful. And Frank has actually was a visionary researcher, and he has predicted that perceptron may eventually be able to learn, make decisions, and translate languages, which was really a visionary prediction at that time. And that is what is really happening. Not that the perceptron is not, but the advanced model of perceptron is eventually able to do these things, what he has predicted more than 50 years back. Then came the multi-layer perceptron, which you can treat as early deep learning model around 1956 to 58 by Alexei. And this is a network of perceptrons. And there was a theorem which says that this can model any continuous or discrete functions. So it is a very, very powerful model. Is there any question? Okay, so limits of perceptron was then introduced in around 1969. So which said that perceptron alone is not really powerful, but then the multi-layer perceptron is very powerful. But this was a kind of a negative impact on the research, that perceptron alone is not really enough for doing hard tasks or solving hard tasks. So there was a long gap for few decades after that, and people have not really bothered about neural networks. So the neural network history, if you look into, there is always ups and downs. And so this was a period where people not have looked. And then from a mathematics side, there was a theorem, and there was this technique called gradient descent came, which was used for these models, training these models. Then around 89, again, some interest started coming, and then there was a universal approximation theorem, which says any any function can be approximated using MLP or multi-layer perceptron. So then again, some interest come, but then it was fairly down again. The interest was not that much. Around 2006, Hinton and his group has come up with unsupervised pre-training, brought some interest again, but the problem was most of these models were requiring a lot of data, which was not there that time, a lot of GPUs or the compute power, which were not cheap that time, right? So as they are today. But after that, the things have started changing, and a lot of compute power has improved, a lot of data has came into the picture, and that has changed things significantly. So in 2012, this is the point where deep learning has started showing promise. There is a task in the computer vision community, which is a visual recognition task. So this model in 2012, which is called LXNet, right? LXNet is a neural network or CNN-based model, which has reduced which has achieved 16% error in ImageNet, right? So this is ImageNet task is given an image, you have to recognize whether it is a cat, whether it's a dog or a car, and so on. So there are thousands such categories. And there are annual contests in this for this task, and this was considered a very hard task during that time. And this method has suddenly jumped. This method suddenly improved the performance and significantly reduced the error rate. And thereafter, computer vision has computer vision, and not just computer vision, but other fields like NLP, speech. Everything has started looking into the problems in the deep learning framework. A lot of new architectures came up, from the VGG and ResNet, and they all have improved the recognition performance and other downstream tasks as well. So this is to introduce how neural network has evolved and over the years. Now, let me briefly talk about biological neurons, right? This is important to understand how concept from a biology has inspired us to think of AI models or artificial intelligence models, which can mimic brain, right? So artificial neurons are like the mimicry of that, right? So which mimics this. So this takes some input x1 to x3, and these are the weighted input, and then it predicts out, right? So this is how the artificial neuron looks like. Well, how does the biological neuron look like, which is inside brain? So of course, I'm not an expert in biology, so I will be not really talking about biology, but too much detail of the biological terms. But high level understanding of this is, okay, there are some dendrites which are connected to the sensors of human body. So our sensors are like eyes and ear and skin, right? So all these sensors are connected to, and they take inputs from these sensors, and then there are some series of things happening here, and finally it sends some signal to the brain to act accordingly, right? So these signals are the outputs. These are sent to the brain, and these XIs are nothing but the inputs from the our sensors, right? And our sensors means eyes and ear and so on. So this is what I was trying to say. You have eye, ear, and let's say skin. This gets some input, and these inputs goes past from these dendrites, and then they give some output, and these output are nothing but these are some signals to the brain, right? Obviously, this is not just one neuron. There are millions of neurons and massively parallel neurons inside our brain. So, and this takes some input. So so for example, if I read some meme, it is a Friday and all my friends are at party, but I am here learning back propagation. So this is some meme about neural network, and I read, and some of my neurons get activated by reading this, right, from my eyes. So it goes this input, and some of my neurons get activated, and it gives a signal to brain, okay, laugh, right? So then we start laughing. With on some other news, which is a sad news, some other neurons get activated, and it gives a signal, it is time to cry, right? So some such things really happen, and this is how the neurons inside. So again, as I said, I'm just talking about the high level picture of how neurons work inside our brain. There are a lot of low level biological or chemical things happening inside, but we're not really interested on that. But in the high level, this is what is happening. Given some input, some number of neurons get activated, and they lead to some signal to the brain, right? So that's a high level picture. So this model of this neurons has like motivated people in the machine learning community or AI community to think about some model which can mimic these neurons, and we can have a computational model for that, right? And with that motivation, people have started designing a computation model for which can mimic the neuron. And this computational model is what is called perceptron. In this module, which is the third module, we'll talk about perceptron. So what is a perceptron? It is a very simple computational unit which does a very simple mathematical operations and gives some output, right? So what it does, it takes some inputs, x1, x2, x3, xn, n inputs, and these inputs are weighted, right? These inputs are weighted and they are aggregated, right? So they are aggregated, and then you have a function f, which is a decision function and which decides something, what will be the value of y. So for now, let's say there is only two prediction it does, binary prediction. Perceptron in earlier model of perceptron can only do a binary prediction, but of course then it evolved. And this xi's can be any real value, and these weights are what is you are interested to learn, and then this is the function, right? So what as I said, this is a very simple aggregation. So what you do is you do the weighted sum, right? So this is the job of G. G is doing weighted sum of inputs, right? 1 to n, there are n inputs, and then this f is checking. This is kind of a nonlinear check, right? So if it is greater than some threshold theta, then I will do this. If it is less than theta, then I am going to do this, right? So y, this means y is 1 or 0. So depending on what, so this theta, we don't know these w's, but otherwise xi's as input, right? So for example, if you are doing some something like, let's say, if I'm going to get a loan or not, right? So let's say that is the task. I'm going to get loan or not, then I will have some features like what is my monthly income, what is my age, maybe what is my gender, and what is my job profile, and so on, right? So there may be a lot of inputs. All these are inputs, and so based, or maybe my past record and so on. So based on this input, I'm going to do, okay, so I'm going to classify, I'm going to decide whether this person is eligible for getting bank loan from the bank or not, right? So that's a binary classification task. And what our simplest model will do, okay, feed all these inputs in some real value and weight them, right? So some of them will get higher weight. For example, gender might not get higher weight because that is not really important for this getting loan or not. But my monthly income is really important. So monthly income might get a higher weight for getting loan, right? So but how do you get that? It's not like you hand engineer these weights, but you actually learn these weights, right? So you actually learn from a lot of data. So this is a simple perceptron. So let's go into a little bit of math. So what I'm going to do now, this theta, I can bring this in the left hand side. So this becomes this, right? So this is simple. Now what I can do is, instead of minus theta, I can write W naught. I introduced one more, and X naught is 1. If I assume this, the equations 1 and 2 written here can be now written as, okay, n will now start from 0 to n, or I will now start from 0 to n, and simply wi xi is greater than or equal to 0, then y is positive or y is 1. If this is quantity is less than 0, then this is 0, right? And this w naught equal to minus theta and x naught equal to 1. This is just to make this arrangement, right? So instead of one more extra variable theta, now what we are going to learn is W0, W1, W2, and Wn. So these weights we need to learn. All right. Let's take a very simple example. How do you learn it? All right. So we have, let's say, input x1 and x2. And the output, what we want is AND of that, right? So this is a binary input, 0, 0, then output is 0, 0, 1, output is 0, 1, 0, output is 0. If they both are 1, it is 1. This is a simple AND gate, right? So AND operation. So, so if we want such output to be classified with some weight, we need to come up with this equation. So this equation are coming from the previous slide, right? So if you remember, if this quantity, the sum, weighted sum, is greater than 0, right? Greater or equal to 0, then so if it is greater or equal to 0, then y is 1, right? So if y, this is y. So y is 1 means this will be greater than or equal to 0. This is just a weighted sum of all the inputs. And these 3 will be less than equal to 0, less than 0, because this y is 0. So these are the 4 conditions. And for these 4 conditions, one has to find right W. Okay? So this, I can also replace this x1 and x2 with the 1 here. So that will come out like this. And I need to get a right W, right? And to get a right W, there is an algorithm called perceptron learning algorithm. Right? So perceptron learning algorithm tries to find right W. What is the motivation of perceptron learning algorithm? Is given this perceptron, what to learn is right W's. That's what we are. If you got the right W, this will do the job. What is really the right W? Let's see. Right. So what I can do is let's do a hit and trial. Right. So hit and trial is like, okay, if I choose W naught equal to 0, W1 equal to 0, and W2 equal to 0, all of them 0, let's say. How many of this will be misclassified? So you can guess. If W naught is 0, this will be misclassified, right? If this also will be misclassified. W naught plus this also will be misclassified, but this will be correctly classified. Right? So whatever in red, they will be misclassified, and whatever in green is going to be correctly classified. So this is just 3 will be misclassified. Very bad choice of W's, right? So this W is not really good. What about if I choose W1 not equal to -1, W1 equal to -1, and W2 equal to 0, some other value, then only one misclassification will happen. All other will be correctly classified. But if I somehow find this particular configuration that W naught is -1, W1 is 0.9, and W2 is 0.9, all of them will be correctly classified, and none of the samples will be incorrectly classified. What does it really mean? So we are just putting some values of W's and getting it right, which is possible for this small configuration. But if you have a lot of Xi's, lot of conditions, that's not going to really work, right? Because in the real world, you will not have this toy example of X1, X2. You will have maybe thousands or millions of variables and millions of conditions. And now in that, you may not able to like hand engineer these things, and you may not able to really pick the numbers like W's, right? So what you really do in practice is use this something called perceptron learning algorithm, right? So perceptron learning algorithm. Before going to perceptron learning algorithm, let's look into how does the error surface look like, right? For this simple case as well. So if you have we have seen this. If this is the W's value, then we make 3 classification. If this is, we make 1. If this, we don't make. So there can be many such values possible. And if you draw it, or if you imagine it in a high dimensional space, this is how the error surface will look like. Your W1 is this, your W2 is this, and this is the error. In this case, it is number of misclassification, but error can be something else depending on the context, right? So the higher the value, the more the error. And this is also denoted in red. The lower the value, less the error, and it is kind of blue, right? So this, the goal is to reach here, right? You can start anywhere, but your goal is to really reach here, because this is where the number of misclassification are list. So this is one type of notation, but the easier notation is also this curve notation, right? So these curve notations are nothing but you take a perpendicular projection of all this, right? So if you just slice it, these are the points where the value of the error is same, right? So inside this, wherever my cursor is, for that values are same. And so this is the place where the value is less, right? And similarly, this is the place where value is large. So error value is large. So ideally you want to reach in where the error value is low, right? So this is curved a way of representing error surface. So now coming back to the how do you really get this perceptron learning algorithm work when you have some training data, right? So you will have some training data which will be like for positive and negative samples. So you will have a set of positive samples. Let's call it y equal to 1, and you have set of negative samples y equal to 0, right? So you have some training data and you want to do learn these weights of a simple perceptron, right? So this is just very simple. What you are going to do is you initialize all these weights using some random weight, right? So you will initialize it with random weight, and then you will do this tail convergence. What you will do, we're going to see in the next slide. Right, so this is what you are going to do. What you are going to do is you will choose one sample, right? So you have a lot of samples, positive samples and negative samples. You will choose one of them first, and then you will check if that is positive, because in training time you know whether it's a positive or negative. If it is a positive, but this quantity is coming out negative, right? This is less than 0. That means that is a misclassification. So you need to adjust the weight. So you are going to adjust it by adding plus, right? So this is W plus X, so that it goes closer to the W's are adjusted. So this is the adjustment of W. Similarly, if it is negative, right, but this quantity is positive, that means you are again misclassifying. This time you are misclassifying a negative sample as positive, right? So then you also need to adjust the weight, and this time you will subtract this with X. So this you will going to do for all the X, right? So this is just very simple for X belonging to Pn, and this you will continue doing for each of the samples you have in your training data, and this update will result in a W which will be which will be a perfect W, or the correct W, which will classify all the samples, positive samples as positive, all the negative samples as negative, right? So so we can classify the linearly separable samples in this, right? So this perceptron is very powerful, and there is a theorem which says if the samples are linearly separable. What do you mean by linearly separable? If the positive samples and negative samples, in between them you can draw some line, so that means they are linearly separable. This perceptron learning algorithm is that powerful that it is guaranteed to converge. means it will classify them, right? So if they are linearly separable, that is the condition. So they can really classify linearly separable samples, but non-linearly separable. So this is, for example, non-linearly separable, right? There is no one line which can separate red dots with blue dots, right? There is no one line. In such case, perceptron learning algorithm will not work, right? And that's a major limitation. So this is a very big limitation that, okay, if the samples are very simply classified, like one is here, one is here, then you can find out a line which can classify positive and negative, but that's not the case in many of the real world scenario, right? Many of the real world scenarios problem is much more complex, and the things are kind of messy like this, and or maybe like so this type of samples. So this type of samples, perceptron learning algorithm cannot really work. So that's a disappointing thing, right? Because the perceptron learning algorithm, very simple one. It works fairly well for linearly separable. It works with the globe. It can give the global solution, it's not the global, but it will classify the positive and negative for the linearly separable case, but it cannot really do anything well for this type of case. It will not converge. It will just, your W will keep on changing, but it will never converge. So therefore, or this is another example of example where things are not linearly separable. So in such cases, a perceptron is not powerful, and that is a disappointing fact. But then there was an idea which came, okay, single perceptron is not really powerful, but what can be done with multi-layer perceptron? So it's just single is not really can do this type of classification of reds versus dots, reds versus blues in this type of input space. But if it is a layer of perceptron, that is very, very powerful, and that can do a lot more than that, right? So this is what our focus of our last module, which is module 4, where we will talk about what is really multi-layer perceptron and how it is trained, right? So this is a theorem which was like a ray of hope, because we have just seen that perceptron alone is not powerful. But now we are seeing, okay, this theorem says any Boolean function of n inputs can be represented by a neural represented by a network of perceptron containing one hidden layer with 2 to the power n perceptron and one output layer containing one perceptron, right? So this is any Boolean function. So that means whatever like binary decision task you can really do with this MLP. But this also has to extend it to not only Boolean, but even continuous functions can be approximated if you have a properly designed architecture. So we'll not prove this theorem, but we will see the practical implication of that. So the network of perceptron will look something like this, right? You will have some inputs and you will have some perceptrons. So those which are in circle, they are perceptron. So so this has multiple layers. One is the input layer, whatever the input is, which can be binary or which can be also real valued. So this is input. There is a hidden layer, like SI is here, hidden layers, and there is an output layer. Y is an output layer. Whichever in circle, they are actually denoting perceptron. Just we have seen the simple perceptron model. These are nothing but that type of model only, like SIs. And you can have not just one hidden layer. You can also have a neural network with multiple hidden layer. But input and output layer will be obviously one. But you can have multiple hidden layers as well, right? So and what are these numbers? W11 is the first input is connected to first hidden perceptron, that is 1, and this is the layer number 1, right? So this subscript is layer number 1. Superscript is layer number. Subscript are the which one is connected to which one. So for example, 2 is connected to 4, so therefore W24, and this is layer number 1. Similarly, this is layer number 2, and these are the neural. So these are the weights, right? And these weights are what you learn in a neural network, right? So this is the goal. These are the parameters which you learn in any neural network. So we like any neural network. When I say there will be always weights, so like it's whatever neural network or CNN or whatever it is, the ultimate goal of any of them is to learn these type of weights, right? So far, what we have seen is this, and again, from the theorem which we just stated, this is very, very powerful. Like this can really do a lot of things. So the thing is, neural network of perceptron or MLP can model any Boolean function. It can model any decision boundary. It can also model any continuous valued function. A lot of things it can do. So, when we say neural network can compute any function. So let's say you have a crazy function like this. You can have some neural network. We don't know which one is the right one, but we can, for sure, there exists some neural network which can approximate the crazy function like this, right? So which is not really very clear. So this is not a closed form solution, is not a closed form equation. It is a very random function, but even this can be approximated with a properly designed architecture of CNN, right? It can also approximate like if the input is vector, not just one, because and the output is also vector, right? So such functions also can be approximated with neural network. And this is more useful because your inputs are not one-dimensional in like X in most of the neural networks for machine learning tasks, right? So your inputs are actually vectors, right? So you have multiple such input and the output is also multiple, right? Not just one, you get this. So such values, such functions can also be approximated. So in short, what is that we are leading to is a neural network is nothing but you have some inputs and you have some output and there is some computation going inside. For a while, even if you don't worry about what computation is, it will be something like this, right? So you have some function. Neural network is nothing but a function now, which takes some input and gives some output, right? This is some function. Now, what is this function doing? We'll see that. But even if you don't know, this is what as a user I can see. If X is the input, Y is some output, and this function is nothing but it is not just a function of input, right? It is not just a function of input, but it is also parameterized function, right? It's a parameterized function of input because this parameter W is what we are interested to learn given some input and output, right? So if your input is, let's say, dog, your output is dog, your input is image of a cat, your output is cat, your input can be some speech audio signal, and output can be I love neural network. Whatever it is just a function of XW, right? So this is f of XW. So we said MLP can represent anything. What is so let's say this is one MLP, and this is some function f of some g of x. So this is g, let's call it g of x. So this g of x is nothing but let's say it represents the class label. Let's assume, right? Let's say it's a cat versus dog classification. So given an image of a cat, there is some class label. Given an image of a dog, there is some class label. Given an image of a cat, there is some class label, and so on. So there are many such images, and you have a class label. You are actually interested to come up with this function, right? So that tomorrow morning, if I have some image, I can really predict what, because if you have approximated this function, then you can really predict whether it's a cat or dog or car or what it is, right? So that is what the goal of MLP is. So this is the automatic estimation of MLP, right? So what it is going to do is you have an input X and you want to predict. So this will do f of XW, right? The f of XW is the task of this. So it will do f of XW, and your goal is to really predict g of x, right? So, or approximate g of x. So what you are going to do is you want to find such w, which is the minima of this, and this is the integration over all x, right? All possible x, and this is divergence. Why it is divergence? Because I want this guy f of x w and g of x both to be closer, right? So this is divergence is actually that. So we want the goal of divergence function is to make them close as possible, and or approximate as possible. And you want to, if the such w, you want to minimize that function, which is with respect to this. And this is integration, by the way, right? Because this is, so far we have not talked about any discrete function. It is a continuous function. So g of x is a continuous function, and this is x, right? So but the problem here is you don't really know gx everywhere, right? Gx on theory it is a continuous function, but g of x is not really known at every place. Why it is not known at every place? Because you do not have access to all the possible images in the world. For example, if we are talking about image classification problem, you will never have access to all possible images in this world, right? So that is an impractical thing that will never happen, because you will have maybe, okay, 1 million, 10 million, whatever it is, but all possible will not be there, right? So therefore, you only have certain data points in this space, g of x. Only some points are known, some xi's and some y's, I hat. Y I hat is the ground truth level. That is known to you, not all, because you have limited data, right? So you have limited data. So therefore, there is no point of making it an integration, but let's make it a summation, which is a discrete equivalent of integration, right? And this is for I equal to 1 to n, because you have, let's say, n training data, and you want to minimize this. So this is the goal of a neural network, right? So the thing is, we want to see, like in a supervised learning framework, how do you learn it? So you have a data where you have xi's, you have ground truth labels, yi's, I equal to 1 to n samples, and each of xi is some feature, right? And each of yi is, let's say, it is positive or negative, but it's not necessarily true. You can also have more labels. For this discussion, we are making it positive and negative. So y equal to fx plus w is the neural network. W is what we are interested to learn. So the model is nothing but y equal to fx w, where f is a neural network. The parameters is w, and w is what we are going to learn, or we are interested to learn. Now, what is the learning algorithm? We have seen one perceptron learning algorithm. We will also see there is something called gradient descent. The perceptron learning algorithm, it works only for one perceptron. Gradient descent is more general, and it can work for any system, right? So, right. So then you also need some loss function to guide this learning algorithm. Let's come to the major problem which we started. So this is what our problem is. Our problem is to find the right set of W, which is the minimum of this quantity. Now, what is this quantity? Let's look into each of them very carefully. There is a first term. So this, let's look into this whole term, right? Because this is just a summation, I equal to 1 to n. Inside this summation, this is the term. So this is called divergence. Divergence is intuitively any function f of ab which has lower value when a equal to b, right? So which has a lower value, so any such function will qualify for divergence. So these are some examples of divergence function. So one is the least mean square, where divergence between these two is just a mean square of this. Or you can have a popular function called cross entropy, which will be written like this, right? So this function will be obviously minimum when these two things will be equal. So this is divergence. What is this f? This f is nothing but a neural network. A neural network is nothing but a parameterized function of input, right? So this is x and w. This is f. Now inside f, x is the input, y is the output, and inside this there are perceptrons. And each of these perceptron looks something like this. So these perceptron are nothing but you have some bunch of inputs, right? And they are weighted, and then you sum over them. So this is just a summation of inputs. And then there is a non-linearity F, which is also getting introduced now. So F and non-linearity along this. So there are also a lot of non-linearity functions like sigmoid, 10H, ReLU, log likelihood. These are like what is popularly used to bring non-linearity in the model, right? So this is important to bring non-linearity in the model. Otherwise, this will be just a linear transformation of things, right? So that may not be enough. So for many of the tasks, so non-linearity is brought from F. Okay, so we have seen what is divergence. Divergence is nothing but some kind of a loss function which try to minimize the distance between these two. F is a neural network, W is the weight, X is the input, and now what is this guy Y hat? Y hat is nothing but the ground truth label, right? So we know what is ground truth label. So how do you represent ground truth label? Let's say if you have a cat versus dog classifier. So this ground truth label Y hat will depend on what is the problem. So if you have a cat versus dog classifier, then you will have let's say image of a cat, and Y hat is just one bit, right? Because you have just two classifiers, so you want one bit to represent them. So you have 0. If it is 0, it is cat. If it is 1, it is dog. So you can represent Y hat is in 1 bit. You can also represent Y hat in 10 bits, right? So here, if it's your classification task is digit classification, your digit will be the input, the image of the digit will be the input, and your Y hat is the output, and this Y hat will be represented by one hot encoding. So this is one hot encoding. If it is 0, my 0th will be 1, all others will be 0. It is 1, so the input is 1, so this becomes 1. If my input is 9, my 9th place will be 1, all others will be 0. So Y hat can be anything, it doesn't really matter. So the thing is, it can be either vector or a single value, so depending on the task. But this, so far we have really learned this function. We know each of these terms now, right? And the divergence can be one loss function. This is a neural network, all these terms we know. Now the goal is to minimize this, right? How do you minimize a function? And to minimize a function, because why minimization is required? Because we want to find such W which can make these two things, F and Y, YI hat, right? These things as closer as possible for the training data, right? Because this is equal to 1 to n. So to minimize such function, you need to go to high school, right? We know from the high school maths how to minimize a function. So we need to just recap what is a gradient, how to minimize a function. So minimizing a function is like you first compute the derivative, and then whenever the derivative is 0, you say it. So this is what it is, minimize, right? So minimum of a function. So here you will have also similar thing. What will happen is first thing is you will have a error. What is that you are going to minimize? You are going to minimize the error surface, right? So you'll have some error surface which can be a multi-dimensional space in the multi-dimensional space. In that multi-dimensional space, you will start at some point and compute the gradient, right? So, and then you will move in the negative direction of gradient. Why negative direction? Why not positive? Because your goal, because the gradient is actually dot product with gradient is nothing but the transpose of derivative, right? So it's a transpose of derivative, and that is nothing but the dot product between the input, change in input, and like gradient, right? If you do the dot product between the gradient and change in input, so let's call the gradient as alpha dot change in input, let's say x. So delta x, alpha dot delta x, then you get delta y, that is change in output, right? So if you multiply if you do the dot product between these two quantity, change in input and the gradient, then you get the change in output. So the thing is, when is the dot product maximum? The dot product is maximum when the direction of both A dot B will be maximum when A is in the direction of B, right? And A dot B will be minimum when A is in opposite direction. So therefore, when the gradient is in opposite direction of change in X, right, there will be the minimum. So that will give you minimum, that will lead to the minimum Y, right? So if you want to reach to the minimum Y, you should always move in the negative direction of the gradient. And that simple intuition or logic or maths has get into this algorithm called gradient descent. So gradient descent, two-line of algorithm. You initialize some parameters like learning rate, 0, and initial weights, and then you compute the this function value, right? So this is f what you want to minimize, the function value with respect to previous iteration and this iteration. If that does not change, you will this, and this is what your weight update is. Your weight is updated, and this is because negative, because you want to move in the negative direction of this gradient, and eta is how much you want to move, right? You want to move just a small bit, or you want to move larger. So that is called a learning rate, and this is t equal to t plus 1 is iteration getting changed. So this is simple algorithm is called the gradient descent algorithm, which is like heavily used for all the neural network optimization. I would say there are variations of this like Bayes gradient descent and so on, but the basic algorithm is this, right? So how does it work? Very simple illustration. Let's say your error surface is this, and you want to minimize, you want to find such W which gives the minimum of this error surface. Then you start at some point, let's say W, right? W naught. You compute the direction of the gradient. As I said, direction of the gradient will be always in the that wherever there is a steep, right? So in always that side, wherever the value will be higher. So this side will be the gradient direction. You will move in the negative of that. So you move here, then again compute the direction gradient. You move here, then you compute the gradient direction. Move here, move here, move here, move here, and go down, right? So this way you reach into the minima. So this is called a gradient descent algorithm. And in gradient descent, now we actually know all of this. Only thing which we don't know, how do you compute this, right? Delta or the gradient itself. Remember, the gradient you are computing is not a function like y equal to x square or something, right? Your function is very complex because it's a neural network, right? A lot of W's are there, a lot of inputs getting changed. And with respect to all of these W's, you are going to compute. So this is not non-trivial. This is not a closed form equation where you compute the derivative and gradient and so on, right? That's not the case. You have a very complex function of a neural network, and there you want to compute this weight. And so for that, there is a technique called backpropagation, which is used to compute gradient with respect to W's weights, right? So this is what is used. I'm not going to discuss this in the interest of time, but if you are really interested, this article in the chapter 2 of this deep learning book has a very nice description of what backpropagation is. But high level thing is backpropagation is what is used to compute this gradient, right, with respect to different W's. So how it works is you start with the loss and you backpropagate the loss and then adjust the weights, right, and then compute this gradient based on that. Once you have this gradient, you can run this for this type of algorithms for a batch, and that is called Bayes gradient distance, or you can do a stochastic Bayes gradient distance to optimize the weights. So in interest of time, let's summarize the today's talk. We have talked about history of the neural network. Then we talked about biological neuron and how we get inspiration from that. We talked about perceptron, which is the basic building block of all the neural networks or even deep neural networks. Then we have seen multi-layer perceptron, how to train it using gradient descent, and how to, we have not seen how to compute the gradient using backpropagation, but backpropagation is used to compute the gradient, and gradient descent is used to find the minima of that error surface. So this is how the neural network has evolved. In the talk, in this workshop, there are a lot of talks ahead, which will be talking about convolutional neural networks, which are like not this vanilla neural network, but convolutional version of that, which also learns the features, not just they take inputs, but they also learns from the features. But the backbone idea is similar. They will have these weights, right? You will have this backpropagation, you will have the gradient descent to optimize that. So the backbone idea remains the same, but how do you convolve in the input, and then how do you compute the output? So the architectures will change definitely, and there are a lot of such interesting talks. I have gone through the program prepared by the organizing team, which is really nice, and you will definitely learn a lot from that. Then a lot of advancement, a series of experts will be talking in this workshop. So with that, I'll end my talk. And if you have, you can ask some questions now itself. If you have more questions, you can contact me. The type of work, what I do, if you want to see, please visit my website. And in IIT Jodhpur, we are looking for motivated PhD students, as well as RA, we have some RA positions as well. So please consider applying. And yeah, if you have any questions, please feel free to ask now. Thank you. Thank you very much.
Yeah, thank you so much, Dr. Anand, for your insightful presentation. And this was really informative. And you have discussed in detail about the basics of neural networks in a very simplistic way. So I would like to tell the audience, if they have any question, they can ask. And also, if you can also send your queries in the chat box, that is also fine, or you can ask.
So there is one question Nandita Ghosh is asking in the chat. So maybe
yeah,
can I respond to that? So sir, at one single iteration, inputs x1, x2 to xn will be different images of cats and dogs, or will it be different features of single cat or dogs? Okay, so the x1, x2, xn will be, if you are trying to model it using neural network, simple neural network, not convolutional. So simple neural network, you can take, let's say, some features. So you can have, let's say, pixel values as feature, right? So your that will be a simplest feature you can think. So you take each of the, because image is nothing but a matrix, right? So you flatten that matrix, each pixel value you take, and that is your x1 to xn. So for one cat image, you will have one x1 to xn. And for another cat image, you will have different cat x1 to xn. So I hope that answers your question, Nandita.
If anyone is having any other question, you can just ask, or you can also post in the chat box, please.
Yeah, so there is another question. Bhaskar Reddy is asking, in deep learning also, we are having supervised, yes. So deep learning is means there are also supervised and unsupervised algorithms. So deep learning is a way to deal with data, right? So it has, this paradigms will be definitely there. Yes. So whenever you have labels, you will use supervised, but if you do not have labels, you will going to use unsupervised. So actually there is a lot of interest in unsupervised algorithms these days. Like you have a lot of data, but you do not have labels, right? So that's there. Yeah, any other question?
Okay, so if you have any other question, yeah.
Yeah, maybe if you have another question, you can email to me. I will also share the slides with the organizing team.
Yes.
And yeah.
Yeah, okay. Thank you so much, Dr. Anand, for this informative talk.